Hello and welcome to the beginning of the end. It is the final module in this physics class, all about electromagnetic waves, which includes visible light and optics. So what exactly is light? That was actually a problem for a long time. We didn't exactly know. We knew it behaved like a wave, and we knew a bunch of stuff about waves, including that they needed a medium to travel through. Whatever the medium may be, water, jelly beans, humans, whatever. There had to be some sort of a medium, air. But we didn't understand how light could get to us from the sun. So at first we just made something up. We said, well, there's got to be some sort of a medium that makes up space. That's not just a vacuum. It's not emptiness. There's something. We have no idea what it is. We can't see it. We can't detect it. But we can tell that it has to be there because light is traveling to us, right? Wrong. So they called it ether, and it turned out to be incorrect. Instead, James Clerk Maxwell discovered that light is just a mutual propagation of electric fields and magnetic fields, creating each other. He did so using Maxwell's equations. Now, these equations actually use some vector calculus, so we're not going to do those. Instead, we're just going to look at qualitatively what they all mean. 1, the field lines always start and end on electric charges. Okay, cool. 2, the magnetic field lines are always closed loops. Okay, and we've seen examples of both of these things in class before. It's these last two that really make a difference. A changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. As they change, as one changes, it causes the other to change. So if I've got an electric field that starts to propagate up and down, as it travels, let's say, to the right, then I'd have a magnetic field that goes out of the page, into the page, out of the page, into the page. A few things about this. The electric field and magnetic field are always at right angles to each other, and they're at right angles to the direction that they're traveling. When you think about the entire electromagnetic spectrum, basically waves that behave this way, it's actually a wide range. Radio waves, for example, have or can have wavelengths that span an entire football field, whereas once you get all the way up to gamma rays in terms of higher frequency, higher energy, now they've got a wavelength that's as small as a single atomic nucleus, which is crazy. So the order of it is just radio wave, that's the longest wavelength, lowest frequency of the electromagnetic spectrum. Then microwave, infrared, visible, ultraviolet, X-ray, gamma ray, getting up to higher frequencies. What's incredible about this is how small the visible light spectrum is, considering the insane amount of the entire electromagnetic spectrum. We really can perceive a very small amount of this type of radiation. Now, all these waves, be them radio or gamma or visible, travel through a vacuum at the speed of light. This speed of light, denoted by the letter C, is 3 times 10 to the 8 meters per second, and that's going to be a constant. Now, as you go to different ranges of the electromagnetic spectrum, you're going to see that, yeah, the wavelength can change, and so the frequency can change, but the speed's going to stay the same, in a vacuum at least. Now, the only reason I can see anything is reflection. So when light strikes a surface, it'll bounce off of it. It absorbs some of that energy, and it reflects some of the other. So something that looks blue, for example, will absorb all the other colors that are hitting it, except for blue, which will be reflected back and smack me in the eyeball. The reason I can't see my reflection because of that is this. If I've got a mirror, it's a really super smooth surface, then the incoming rays bounce off at the same angle as the outgoing rays. Versus most objects have surfaces that aren't quite that smooth, and they just bounce off in all sorts of random directions. But that's just when light's traveling through, air or a vacuum. It starts to get more interesting when light's traveling through different materials. In fact, light will actually slow down as it goes through, let's say, water or glass or something like that. Any material that transmits light, that allows it to pass through, has what's called an index of refraction. And that index of refraction is just a ratio of velocities. It's the speed of light in a vacuum divided by the speed of light in that material. And since it's just a simple ratio, it is unitless. So when you get these materials, you just get a number for their index of refraction. From that number, you can tell exactly how fast light is traveling through it. And that's not all. You can also tell how much light will bend as it passes through that surface. So things get really, really, really interesting when you're traveling through one material of a certain index of refraction, and then you hit another material with a different index of refraction. You get what's called refraction. Oh, and it's just the bending of light. To figure out how much the light will bend, you can use what's called Snell's law. So you start with an incoming ray coming in at an angle of incidence. Now be aware, this angle of incidence is not the angle between the light ray and the surface it's about to strike. Instead, imagine if you've got your surface, or your barrier between your two materials, imagine a little dotted line 90 degrees to that surface. However far away the incoming ray is from that imaginary 90-degree line, that is considered your angle of incidence. And the outgoing ray is the angle of refraction. Same sort of deal. Keep that dotted line going through both materials at 90 degrees to that surface. And theta 2, or the angle of refraction, is also going to be relative to that. And Snell's law is simply n1 sine theta 1 equals n2 sine theta 2. So the index of refraction times the sine of the incident angle equals the index of refraction of the new material times the sine of the refracted angle. Nice. Now if something's translucent, like a plastic cup or a beaker or a window or something like that, some of the light that strikes it will get reflected, some of the light that strikes it will get refracted and transmitted, which will allow it to pass through. It gets even more interesting when you pass, say, pure white light through these things. Every material has a slightly different index of refraction for different frequencies of the electromagnetic wave. Now, for some materials, it's barely different at all, that you wouldn't even be able to notice it. But for some other materials, it's a lot more pronounced. So this will cause purple light, for example, to bend a lot more than red light. And that's what's called dispersion. So as white light strikes this prism, then it starts to separate inside the glass prism, and it separates even further when it travels out of the glass prism and back into the air, which actually is how rainbows work. If you imagine a tiny little rain droplet with an incident ray coming at it at some angle, when that ray strikes it, it'll bend differently with its different wavelengths, slightly. And it'll start to spread out into a little bit of a rainbow shape inside that rain droplet. This slightly dispersed light, some of it will refract back out the other side, and it still might not be quite spread out enough for us to observe a rainbow. Could be, could not be. Or it'll bounce off the backside of the rain droplet and start heading back toward the front of it again. At which point it will refract back into the air, and by that point be spread out enough for us to see all the beautiful little colors of the rainbow. And the final phenomenon we're going to talk about in this video, at least, is total internal reflection. Here's how it works. It only works when you're traveling from a higher index of refraction to a lower index of refraction. So let's say, for example, I'm shining a laser beam from water out into air. Water has an index of refraction of about 1.33, and air has an index of refraction of about 1. So as I shine my laser beam from underwater up toward the surface, it'll refract, and it'll do so in such a way that when I look at the angle from the 90-degree mark to the surface, I end up with an incoming angle that's smaller than my outgoing angle. And that's simply because my incoming index of refraction is bigger than my outgoing index of refraction. And Snell's law still needs to work. If I change my angle, if I increase theta 1, I'll increase theta 2 as well, the outgoing angle. And eventually I'll get to a point where the laser beam doesn't even leave the water at all. It ends up with what would be a refracted angle of 90 degrees. At this point, my incident angle is known as the critical angle, right where theta 2 equals 90 degrees and does not leave the first surface. At that point, you get no refraction out, you get only reflection. So you can calculate the critical angle pretty easily using Snell's law. N1 times sine theta 1, or theta critical, equals N2 times sine of 90 degrees. That is it. So any angle bigger than the critical angle will produce total internal reflection. This actually is how fiber optic cables works, like Verizon Fios. Right? You have a cable that's actually consisting of two different materials, an inner core and an outer thing called the cladding. The core has a higher index of refraction than the cladding, and the idea is if you send a signal down, it'll just bounce around the core and not actually leave the surface. So you can send signals at really, really ridiculously high speeds through fiber optic cables. And that's about it for this video. Take it easy.